Alright, measures of dispersion. In the first set we just did, the measures of central tendency were very similar. We got 10, 10, 10, and 9.5. In the second set we saw that the averages didn't agree so much. We had 50, 10, 10, and 184.5. In the last set, the mean, median, and mid-range all agreed, but if you look at the data, there weren't any 10s anywhere in that data, so the 10 wasn't really representative of the data. In all of these cases, it's good to have a measure of dispersion. A measure of dispersion, or measures of dispersion, are used to measure the variability and how the data is spread out from the mean. The range is going to be the difference between the highest and lowest values. So that's kind of like the mid-range. It's just the range that's not been cut in half. The standard deviation measures how much the data differs from the mean. It is signified by S for the sample set, or by a small sigma for the population. To determine a sample set's standard deviation, first we need to determine what the mean is. Then we'll make a chart with 3 columns. First will be each item of data. Second column will be the difference between the data and the mean. And the third column will be the square of the second column. Data minus mean, the quantity squared. Then we'll list the data, calculate the second column by subtracting the mean, calculate the third column by squaring the second column. Then we'll determine the sum of the third column. We'll add up all the data in the third column. We'll divide that by 1 less than the number of items. And once we've done that division, we have what we call the variance. Then we'll take the square root of that number, and that will be the standard deviation. So let's practice. Obviously I'm not going to give you practice with hundreds of items. We have calculators and computers that do that kind of thing for us. So we'll just do some simple examples. If we add up these and divide by 6, we'll find we seem to be running into a lot of means of 10, but we'll find that x bar is 10. So we'll build a table, put all of our information in it, and then we'll find the difference between each of these data points and 10. So 4 minus 10 is negative 6, and that's just fine for us to have some negatives. In fact, you'd better. 8 minus 10 is negative 2. 9 minus 10 is negative 1. 11 minus 10 is positive 1. 13 minus 10 is positive 3. 15 minus 10 is positive 5. Alright, now let's square each of these. 36, 4, 1, 1, 9, 25. At this point we'll add up all of these values. 36 and 4 is 40, plus 10 is 50, 75, 76. Now, since there are 1, 2, 3, 4, 5, 6 items, the number we're going to divide by won't be 6, but it'll be 5. So 76 divided by 5 is 15.2. And again, this is the variance. To find our standard deviation, we'll take the square root of 15.2, and that is approximately 3.90. Let's do the next set. 7, 9, 7, 9, 9, 10, 12. Alright, when we take the average of those, the x bar will be 9. We'll bring up our table with 7, 7, 9, 9, 9, 10, 12. Notice that the median would be 9 and the mode would be 9 also. The average is 9. I get the feeling 9 is a pretty good indicator of what this set of data tells us. We'll subtract 9 from 7 and again, and we get zeros. 10 minus 9 is 1, 12 minus 9 is 3. Then we'll square all these numbers. 4, 4, 0, 0, 0, 1, 9, and add them up to get 18. Since there are 7 items, we're going to divide the 18 by 6, one less than that. And 18 over 6 gives us a 3, so that's our variance. And then we'll take the square root of that, and that's our standard deviation. You might notice that on this, with this set of data, where they're all pretty well clustered together, the furthest away we get from 9 is this 12 up here. We have a standard deviation that's less than 2. In our previous one, we had a standard deviation of 3.9, and like the 4, that's pretty far off from the mean, from 10. And the 15 is pretty far off from the 10 also. So the further away your data values are, the more spread out they are, the higher the standard deviation will be. Okay, determine the standard deviation for the following set of data, round to the nearest hundredth if necessary. And if we add all of these values up and divide by 2468, we will see that the mean is 170. So we'll start subtracting. 95 minus 170 is negative 75. Fortunately, we only have to do that math once. 129 minus 170 is negative 41. 158 minus 170 is negative 12. 175 minus 170 is 5. 180 minus 170 is 10. 288 minus 170 is 58. And, oh, that's not 58. That shouldn't be 288. That's a typo. That's 228. And 300 minus 170 would be 130. This data looks pretty spread out. I'm guessing it's going to have a larger standard deviation. Now, the fun begins. 75 squared is 5625. And that's duplicated. 41 squared is 1681. 12 squared, something nice, 144. 25, 100. 58 squared is 3364. And 130 squared is 16,900. And if we add that all up, we get 33,464. That's going to give us a huge variance. And notice that over half of that is right here in this last one. We call that an outlier when we have one that's just way far out of the ballpark. Alright, we had 8 items, so we're going to divide by 7. We'll take one away from that to get 7. We'll take the 33,464 divided by 7. Again, that's our variance. And that's approximately 4,780.57. And then our standard deviation will be the square root of that ugly number. And I get that that's about 69, a little bit more than 69, 69.14. And I believe that. I can see that the standard deviation would be about 69.14. These are a little more than 69 off. This is right at twice 69 off, so the deviation is there.